You know how your computer just works? You've got music streaming, a file downloading, a dozen tabs open, and it all happens at once, without a hitch. It feels so seamless, right? Well, underneath that smooth experience is this hidden, incredibly complex world of workload management. So today, we're going to pull back the curtain and see exactly how your operating system is juggling all of that at once. First up, we'll talk about the grand illusion of multitasking that we all see every day. Then, we'll get into the nitty-gritty of the juggling act that makes it all possible. After that, we'll look at the scheduler's rules, basically how your computer decides what to do next. We'll cover the hardware advantage of modern chips, touch on the dangers of sharing data, and finally, wrap it all up with why this matters to you. All right, so let's start with what we all experience. This perfect, parallel world where everything seems to happen at the exact same time.
I mean, just think about your desktop right now. You might have your browser going, a video call up, maybe a spreadsheet open in the background. It feels like each one of those apps has its own private, dedicated machine, doesn't it? But that's the illusion. To understand what's really going on, we need to get a couple of key terms down first.
Okay, first up is something called a process. The easiest way to think about a process is just a program that's running. Your web browser, that's a process. Your email client, another process. And the absolutely crucial thing here is that the operating system builds a virtual wall around each one, giving it a private, protected memory space. This is huge for security. It's what stops a buggy game from crashing your whole computer or a shady app from snooping on your online banking. Now, inside each of those processes, you can have even smaller units of work called threads. So stick with the browser example. One thread might be loading a new web page, while another is playing a YouTube video on a different tab. And because these threads are all part of the same parent process, the browser, they can all share the same memory. This lets them work together super efficiently. So let's just quickly break down the difference. Processes are like separate independent houses. They're walled off from each other for safety. Threads are more like roommates living in the same house. They share the same space and resources, which makes them really lightweight and collaborative. This whole process versus thread distinction is totally fundamental to how modern software gets built, for both performance and stability. Okay, so if only one thing can really happen at a time on a single CPU core, how in the world does the operating system create this amazing illusion of doing everything at once? Well, it all comes down to an incredibly fast and clever juggling act. This is the secret sauce. It's called time slicing. Your CPU runs a tiny piece of one program, then in a flash, it performs something called a context switch. It saves all its progress, immediately picks up a different program, works on that for a few milliseconds, switches again, and on it goes. This happens so unbelievably fast. We're talking thousands of times every second, that to our slow human brains, it looks like everything is running in perfect parallel. But here's the catch. This juggling isn't free. Every single one of those context switches takes a tiny bit of time and energy. This analogy really hits the nail on the head. The act of stopping one task, saving its state, and loading up the next one is what we call overhead. It's work the computer has to do that isn't your work. So a huge part of an operating system's job is to make that switch as blazing fast as possible. Okay, so this brings up a pretty obvious question, right? If you've got hundreds of processes and maybe thousands of threads all screaming for the CPU's attention, how on earth does the operating system decide who gets to go next? Well, the answer lies in this really critical part of the OS called the task scheduler. You can think of it as the ultimate air traffic controller for your CPU. It uses a set of very smart rules, a scheduling algorithm, to make sure every task gets its fair turn, but also to prioritize the important stuff. To make sure your video call stays smooth even when your email is syncing in the background. Now, to manage all this chaos, the scheduler keeps a little dossier on every single process. It's called a process control block, or PCB. Think of it like a passport for a task. It holds all the vital stats: what it's currently doing, is it ready to run or is it waiting, its unique ID, its priority level, and a perfect snapshot of the CPU state. This is what makes that context switch possible. It's how the OS can pause a task and then resume it later as if nothing ever happened. And here's where it gets really smart. The scheduler doesn't just have one long line of tasks waiting. It sorts them into different queues based on what they're doing. If a task is ready to do some math, it goes in the ready queue. But if a task is stuck waiting for something slow, like reading a file from a hard drive, it gets moved to a separate wait queue. This is brilliant because it stops the CPU from wasting precious cycles on a task that's just sitting around twiddling its thumbs.
So everything we've talked about so far is really about creating an illusion of doing things in parallel on a single processor core, but our modern computers have a massive hardware advantage that turns that illusion into a reality. This analogy is just perfect. On an old single-core CPU, multitasking is like having one incredibly fast chef frantically jumping between a bunch of different recipes. But with today's multi-core CPUs, it's like having multiple chefs in the kitchen, each one working on their own recipe at the very same time. That is true parallelism. Multiple threads are literally executing simultaneously on different physical cores. And it gets even more clever than that. There's a technique called simultaneous multithreading, which you might know by its brand name, hyperthreading. The basic idea is to squeeze every last drop of performance out of each core. If one thread has to pause for a nanosecond, maybe it's waiting for data to arrive from memory, the CPU hardware can instantly slot in instructions from a second thread to keep the machinery busy. It's all about filling in the gaps and making sure no resource ever sits idle. But as you can probably guess, this world of true simultaneous execution, well, it creates a whole new class of very tricky problems, especially when multiple threads all need to access the same chunk of data. Seriously, just pause and think about that for a second. Let's say you have two threads that both try to update your bank account balance at the exact same microsecond. What's the result? Does one overwrite the other? Does the balance just get corrupted into nonsense? This is legitimately one of the hardest problems in all of computer science. This scary scenario is called a race condition. It's when the final outcome of your program depends on the totally unpredictable timing of which thread gets to the data first. It's a race, and the loser is your data's integrity. These bugs are an absolute nightmare for developers because they might only happen once in a million runs, but that one time could be catastrophic. So, the solution is to write code that is thread-safe. What that means is that the programmer has to be incredibly careful to build in protections, things like digital locks, that guarantee only one thread can touch a piece of shared data at a time. It is a true art form, making sure that even in this chaotic world of parallel execution, the results are always correct and predictable. Okay, so we've gone from the smooth user experience all the way down to the silicon and back up to the challenges of programming. Let's tie this all together and talk about why this hidden world is so incredibly important. At the end of the day, it's this. That strict separation of processes, those virtual walls, that's what keeps your banking information safe from other apps. And those intelligent rules the scheduler uses, that's what makes your whole system feel snappy and responsive, ensuring your video call doesn't freeze just because an update started downloading. Every single part of this complex dance is designed to give you a powerful, stable, and secure experience. And that kind of leaves us with a big final thought. For decades, the name of the game in computing was just speed, speed, speed. But now that we have chips with 8, 16, even 32 cores, the game is changing. Maybe the biggest challenge for the next generation of computing isn't just about raw speed anymore. Maybe it's about finding ways to safely and efficiently manage the incredible complexity that all this power has created. Something to think about. Thanks for joining me.